In this video, we continue with the explanation of osmotic pressure by examining what happens when you're beyond the ideal case. Alright, in the last video, we have derived what the equation for osmotic pressure is. And we have seen that the osmotic pressure has a linear dependence with the molar concentration of the solute. Okay, this is the expression. There is a main approximation in the derivation of this equation, and that is that the solution has to be ideal dilute. But when you make this solution, say suppose that you're mixing hemoglobin with water to make an experiment with laboratory blood, you actually don't know if the 10 grams of hemoglobin that you're dissolving in 1 liter of water, for example, if that is going to be dilute enough that we can guarantee that this equation is going to be operative or not. Right, so because we don't know if we're in the ideal case regularly, our question is, well, what happens if that approximation breaks down and we cannot use this equation directly? How do we deal with that problem, with deviations from ideality? Something that occurs quite commonly is that you like to respect the shape of this equation and try to modify it so that you can incorporate deviations from ideality. Now, when you look at this expression, you will be deviating from ideality if the molar concentration that you're handling is large. So one way to proceed and incorporate here terms that allow you to correct from deviations from ideality is to add terms that depend on increasing powers of this molar concentration. So a way to modify this equation straightforwardly is to say, well, this equation that we just have derived is just the first term on an expansion that depends on the variable that is more likely to break than the approximation. Okay, so again, here we're going to be including terms that depend on increasing powers of the molar concentration, and again, we hope that those can capture deviations from ideality. Without the presence of these terms, right here we actually have not modified the expression at all, so this would still be the ideal case. Right, so to modify this, what we can do is say, well, this is going to be equal to a constant times the molar concentration of B plus another constant that I'm going to call constant prime times the concentration of B squared plus another constant times the concentration of B cubes, and you can continue to do this until your heart's content. Principle you can have here a sum of infinite terms. And again, if you're in the ideal case, then what will happen is that this constant will be 0, that constant will be 0, and all of the constants that you have right here, all they all will be 0. Okay, but if not, then these constants will allow you to incorporate deviations from ideality. Now the main question here is how can we still derive the molar mass, how we can obtain the molar mass from this expression. Again, remember that the molar mass is contained in the molar concentration, okay? Because the molar concentration is simply the mass concentration over the molar mass. Okay, so that molar concentration is equal to the mass concentration, C sub B, over the molar mass of the solute. Okay, and this is going to be equal to 1 plus this constant times the mass concentration of B over the molar mass plus this constant prime Cv over molar mass squared plus more terms, cubic, quadratic, and so forth. Okay, so here's where the molar mass would be. Alright, we're going to modify this expression further by dividing everything over the mass concentration, just for it makes things a little easier. Okay, so if we divide over the mass concentration, this is going to be equal to RT over the molar mass of B, multiplying 1 plus constant Cv, the molar mass of B, plus constant prime Cv, molar mass of B squared, and again all of those terms. Okay, and finally what we can do is just operate through the parentheses and see what results here. Osmotic pressure over the mass concentration is equal to RT molar mass of B times 1 plus RT over the molar mass of B times this constant mass concentration of B over the molar mass of B, so that will be molar mass of B squared, and then we'll have this constant prime RT times this constant prime times the mass concentration of B squared divided over the molar mass of B divided over the molar mass of B squared, so that will be molar mass of B cubes plus all of these terms. Okay? And again, that expansion would continue until infinity. And again, the question still remains, how do we actually calculate this molar mass? That is our variable. What type of experiments can we do, and how can we analyze them to calculate that molar mass? Okay, so the way that we actually are going to show how to calculate the molar mass is graphically. Okay? Notice that you can actually plot this equation by doing the following. The experiments that you're going to run is you're going to be measuring the osmotic pressure as a function of the mass concentration for various experiments, right? So you can make a max concentration of, say, 1 gram per liter, and then 2 grams per liter, then maybe 4 grams per liter, then maybe 6 grams per liter, and then you can measure the osmotic pressure for each one of them. Okay? The way that this equation looks is we can actually assume that this is just a polynomial in which the y-axis will be this, the osmotic pressure over the mass concentration, then that simply is a constant, and then our variable would be this mass concentration, so that will be plus m times x plus another constant which we're going to call n times x squared, and then you will have here another term that is x cubes and x fourths and so forth. Okay, so notice that what you have to do is represent in the y-axis, you have to represent the osmotic pressure over the mass concentration, and in the y-axis, you have to represent the mass concentration. Okay, so let's plot how this graph would look like. There is osmotic pressure over mass concentration, and this is mass concentration. Right, so let's analyze here how we can get the osmotic pressure, not the osmotic pressure, but the molar mass from this representation. We now assume that we're back in the ideal case, and then that means that this constant is 0, that constant is 0, and all of these terms are 0. What that means is that, well, the value of the osmotic pressure over the mass concentration is simply a constant. Okay, notice that that does not depend on the mass concentration, so these 4 points would actually look like this. 1, 2, 3, 4. You can fit that, and it turns out that the intercept with this axis is exactly RT over the molar mass of B. Okay? Notice that in that equation, the m constant will be 0, n will be 0, and all the terms will be 0. Then what that means is that the intercept of this fit with the y-axis will be RT over the molar mass, which is what we have right here. Okay, so that will be the simplest case, the ideal case. You can actually obtain the molar mass with just one of the points, as we have seen before. But then what happens is this: if this solution deviates from ideality, how we would actually do that? Well, various things can happen, right? For example, it might be possible that you deviate from ideality, and that is captured by this term right here that has a non-zero value, but the rest of terms have constants here that are 0. In that case, then, when you represent that data, the osmotic pressure over the mass concentration versus mass concentration, if this term is not 0, but the rest are 0, then you're looking at the equation of a straight line, y is equal to a plus mx. Right? So the way that this equation is going to look like is something like this. You will get a point like here, 2, 3, and 4. Now you can fit that point, okay, and you're going to get 2 variables. One of them is the intercept with the y-axis, and the other one is the slope. Well, the intercept with the y-axis, which we can plot right here, okay, notice that intercept is still going to be RT over the molar mass, right? So for from the intercept, you can obtain what the molar mass is. The slope of this line is going to be equal to this RT over the molar mass squared times this constant. Okay, so in principle, you could also obtain what the molar mass is from the slope, but you actually would need to know what this constant is, and we don't know what that is. It's just a measure of how far away from ideality you are, and we in principle would know how that is. All right, so that would be a second case. A third case would be one in which you deviate from ideality, but instead of having just one correction, you actually have to add 2. So you will have a linear correction and then a quadratic correction, and the rest of the terms will be 0. So then what happens here is that, well, the way that your data is going to look like might be like this, then like that, and like that. Okay, so now you have to fit that to a second order polynomial, but what will happen after fitting that to a second order polynomial is that the intercept with this axis is still going to be RT over the molar mass. Okay, so again, notice that this, in principle, you can continue to do this and fit it with a cubic form, fourth order polynomial, fifth order, and all of the orders that you need to fit the data. Okay, of course, you will need many more points to go beyond a third order polynomial, but the common element in all of those fits, and that what is important here, is that the intercept is always going to be equal to RT over the molar mass. And that means that, well, you know what the temperature is, R is a constant, you can always obtain what the molar mass is from the intercept. Okay, so this is an example of how you can take an ideal expression, that for osmotic pressure, and then modify it by incorporating terms that account for deviations from ideality. Okay, in that case, to determine the molar mass of your substance, then you need to do more than one measurement. Okay, but graphical representation of those various measurements allow you to do a fit, and in that fit, the intercept with the y-axis, if you plot the osmotic pressure or the mass concentration versus mass concentration, is always going to be RT over the molar mass. Okay, so this video finishes our series on the thermodynamics of non-electrolytes, and in the next chapter, we're going to be taking a look at the chemical equilibrium.